Chapter 21. The goal in this chapter is to apply the first law of thermo and the second law of thermo to devices used to transform heat into work. So let's kind of remind ourselves, first law, second law. Now the way we're using the first law, we're saying that the change in energy of our system is due solely to a change in thermal energy of our system, which is due to heat flow in or out plus work external. Okay? The second law of thermodynamics says most macroscopic processes are irreversible. In particular, heat always flows spontaneously from hotter objects to colder objects, and never from colder to hotter. In this chapter, our perspective is going to change a little. Up until this point, we've been concentrating on looking at how the thermal energy content of our system has changed. Okay? Now we're going to start looking at how much work we can get out of our system. Okay? So we're going to change our emphasis a little bit. Right now we've been looking at work external as minus P delta V, where work is positive if work is done on the system and work is negative if it's done by the system. Since we're going to be interested in heat engines and worried about the energy coming out, and refrigerators, the energy that we're having to put in to drive something, then we're going to start looking at W sub S, work for the surroundings. How much energy is flowing out as work to the from the point of view of the surrounding, what's happening. So work, W sub S, is positive if the system is doing work on the surroundings, so it's energy going out to the surroundings. It's negative if it is going into the system, coming out of the surroundings. So WS is equal negative of W external. Okay? So guys, that means that our change in thermal energy is equal to Q plus W external, or it's equal to Q minus W sub S. Okay, let me move this over here so to kind of remind you. Okay, up the top, that's where we've been. The one I've got boxed in there, that's where we're going. Okay. Okay, so again, change in thermal energy is Q plus a minus WS, or Q minus WS. Now, if I start kind of working with this, rearranging it a little bit more, okay, I can say WS plus change in thermal energy is equal to Q, or I can say Q is equal to WS plus change in thermal energy. Now guys, one of the ways we can read this is that if I put heat energy in, I can get some of it out as work, and some of it's going to change the thermal energy of the system, and I can't avoid it. Okay? So any energy transferred into the system as heat is either used to do useful work or is stored in the system as an increase in thermal energy. So, important equation. So on a PV diagram, WS is going to be the area under the PV curve integrated from initial to final, not the negative like we did for work external. Okay? So, PV. So if I started out at a point here, my initial point, point 1, and I've got a point here, a point 2, 0.2. Okay? So if I went from 1 to 2, the area under here would equal WS, okay? Work external would be the negative of the area under that curve. Remember, it's all a matter of perspective. Okay. Now let me erase. And let's go back. So, excuse me a minute here, guys. Erase. There. Yes. So, let's look at adding energy transfer diagrams to our arsenal of ways to examine energy transfers in and out of the system. Okay? Now, as we start to talk about heat engines, we're going to talk about heat reservoirs. Okay, heat reservoir is an object or part of an object to which we can add some heat energy or remove some heat energy, and the temperature of the object will not change. So if I were to light a candle in this room in the next 10 minutes, the temperature of this room is not going to change from me lighting that candle. Okay? So the ocean could be thought of as a heat reservoir. We talk about hot reservoirs and cold reservoirs. The hot reservoir is going to be our high temperature reservoir. Our cold reservoir is our low temperature reservoir. QH is the heat flowing from or to the hot reservoir. QC is heat flowing to or from the cold reservoir. A system is either going to be our heat engine or a refrigerator. WS is the work from the point of view of the surroundings. So let's look at a pictorial representation here of a copper rod. Okay? Heat is transferred from hot to cold here. So QH is coming in here at the hot side, and QC is heat energy going out at the cold side. In this case, everything that's flowing in at the hot is flowing out at the cold, and the change in thermal energy is 0 when work is 0. Okay? So if I drew an energy diagram for this, it will look like this. Energy coming on from the hot reservoir is going into the system, and all of that energy is going out of the system into the cold reservoir. So transferring heat from a hot reservoir to a cold reservoir, no big deal. Now let's think about a process of transforming work into heat. And the question that we can ask is, can we 100% convert work into the system into heat out of the system? So if I were to take a rock, let's say, and I were to rub two rocks together and dump it into the ocean, and then pick the rocks back up and rub them together and then dump them into the ocean and keep repeating it. Okay? We would have a energy diagram that looks like this. Work in, heat out. You can 100% take work and convert it into heat. It's possible. Now we ask the question, can we convert 100% of work into a system? Well, we already talked about that. We can. Now let's consider the opposite. Can we convert 100% of the heat in a system into work out of the system? Okay? So let's take a piston, trap sample of gas, very insulated, except here on the bottom where I have it connected to a hot reservoir, and I put masses on here. Okay? So it started out down here, and as we heated up the gas, it lifted the piston. Now, if I start taking these little blocks off, what's going to happen with the piston? Well, there's going to be less pressure on the outside than on the inside, so the piston is going to keep trying to move up. Well, the sides here aren't forever. I pull all of these up, this piston's gonna blow. Okay? So it lifted the piston, the gas is no longer in the state it was initially at. And if I take these out, I'm really messing with things. Heat flows in, the piston rises, the weights are lifted. When we do this and we remove the weight, if the piston was not secured, the piston would move higher and would pop out. Even if we put a pin in and we remove the masses, the piston is now at a different position than it was at the beginning of our process, and there is fast moving gas inside that piston. The system has not returned to its original state, which means that energy is being stored in the system. The thermal energy of the content of the system has changed. Not all of the energy that we put in heat was used in lifting the blocks, so there's energy left in. Okay, now, this is important. To be a useful heat engine, okay, it has to be able to return to its original position, its original pressure volume point on a PV diagram, so that the process can be repeated. So in the piston we were just looking at, this guy. If I put a pin in here and I lift these guys off, I am not back to where I was when I began with. If I was going to do that, I would have to somehow suck some thermal energy out of this so I could reset. Okay? To return that system back to its original starting point, we'd have to turn off the gas and let it cool and let the volume decrease. We'd have to put it, maybe sit it on an ice block to suck energy out so that we could bring the process back to its initial point. So let's think for a minute. If we deliver to a system by way of heat, the kinetic energy of the gas particles on average increase. This means that they're in random straight line motion and they're moving more. And only a fraction of the gas particles at a moment in time are colliding with the piston and doing the lifting. The rest of them aren't doing any of the work. So only that fraction of the particles that are hitting the part of the piston are ever going to do work. Okay? Do the lifting. So it's going to be dependent on how much work I can get out, how much lifting is going to depend on how the surface areas of the piston compared with the walls and the bottom, and as it changes, it changes. Okay? So, an important fact here to remember is as we're getting ready to lift, we can't access all of the energy to lift because not all the particles are moving in the same direction at the same time. And statistics of large particles tells us that it's very, 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 very unlikely for all of those particles to be moving toward the piston at the same moment, at the same time. So it's an important fact that to lift something, we also need to be able to lower the piston again. So we need a way to suck the energy out, and we're going to have to suck it out as heat to a cold reservoir. So a working heat engine is a cyclic device that must return to its original state or the machine is useless. For a heat engine, work out is always going to be the difference between energy flowing in from the hot reservoir and heat flowing out to the cold reservoir. The thermal efficiency, eta, of a heat engine is always equal to work out divided by QH. And we can calculate eta as 1 minus QC over QH. A heat engine's efficiency can never be 1 or 100%. Because to be 1, there would be absolutely no heat exhausted to the cold reservoir. All of the heat would be transferred out of the system as work, and that's just not possible. So we're going to look at page 593. We're going to look at conceptual problem 2, and then we're going to look at problem 9 on page 594. So we're going to look at page 593, conceptual problem 2. Okay. Must be okay, now let's look at conceptual problem 2 here. It says rank in order from largest to smallest the amount of work WS1 to WS4 done by the gas in each of these cycles. Well, we're thinking about the energy in the area inside. So this is 1 by 1, 2, 3, so we can call that area 3. The area here is 1, 2, 3 by 1, 3 here. So these two cycles are going to give me the same amount of energy out. Okay? If I look here, I've got 1 half of 1 by 3. So this one's half of that. So 4 is less than 1, which is equal to 2. And if I look at the third one here, I've got 3 by 3, that's 9. Half of 9, that's 9 halves. This one's the most energy out. Okay? So 4 is the smallest, 1 is next, which equals 2, and 3 is the largest. Okay? One of the things I want you to notice here is that if I look at this PV diagram and we follow the arrows, notice that you're seeing a clockwise cycle. Okay? Clockwise cycles are associated with heat engines. Counterclockwise cycles are going to be associated with refrigerators. Now, the other question that I wanted us to look at here was problem 9 on page 594. So let's flip over to the next page. Okay, so let's read the problem and then we'll go to the graph. It says cycle shown in 21.9 consists of 3 phases. Make a table with rows and label them A through C and columns labeled change in thermal energy W, S, and Q, and fill in each box of the table with a plus, a minus, or a 0 to indicate whether the quantity increases, decreases, or stays the same during the process. Okay? So let's blow this up a little bit. All right. Now I'm going to do the table, talk you through it, and then I'll flip over here and we'll show it. So we've got process A, process B, process C. I want to talk about the change in thermal energy, the change in Q, and WS. Okay, now when I look at B, let's start off real easy. We know that that's a isochoric process. The volume stays the constant, so there's no work done. Okay? Now, if I look at process A is adiabatic. So I know that Q is 0. Because in an adiabatic process, no heat flows in and out of our system. In C, it's isothermal. So I show the change in the thermal energy is 0. Okay? Now, in process A, we have an expansion. It's increasing in volume. So the work from the point of view of the environment, WS is positive, because work external remember, which is minus P delta V, kind of thinking about it, it would be negative because our change in volume is increasing. So work WS is positive. Okay? B, if I look at C, now it's compression. Because it's a compression, work external from the point of view of the system is positive, WS is negative. So A, energy is coming out, C, energy is being put back in. Okay? Now, if I look at it and start thinking about our equations, let's remind ourselves. I'm going to flip back here for a second. Let's see, where am I pretty? I'm going to look at this pretty little chart here. In an isochoric process, okay, isochoric, there is no work done and heat flowing in has to be equal to the change in thermal energy of our system. Now, if we look at our processes A, B, and C, then change in thermal energy is going to equal change in Q. The pressure went up, so heat energy had to flow in because Q equals N C sub V delta T. The pressure went up, the temperature is going to go up. So Q was positive on B, change in thermal energy is going to be positive on B. Now, C was isothermal. So Q is going to equal to S. So our Q there is negative. A was adiabatic. So heat was 0. Change in thermal energy is minus WS. And in A, WS was positive, so the change in thermal energy of our system was negative. Okay? Now let me show you the picture again, and then I'm going to show you my chart. Okay? So there's the pretty picture. Okay? Here's my chart. So for A, B, and C, change in thermal energy, change in Q, WS, and I just put work external just to kind of keep us on the straight and narrow. So if you think about work external and WS being the negative of work external, okay, it may help you out some. All right. Now, you think about QC, you can think about it as being the waste heat, that portion of the thermal energy that could not be converted into work. If we think about it to convert all the heat energy, all the gas particles would all have to be moving in the same direction at the same time. So we're going to look at stop and think on page 574 in your textbook. think here. What it says is rank in order from largest to smallest the work out performed for these 4 heat engines. Well, all I have to do to get work out is subtract work QC from QH. So here I have 40, here I have 40, here I have 30, and 90 minus 40 is 50. So largest amount is D, and then C, and then A and B are equal. Now for each one of these, I can calculate its thermal efficiency. And I'm just going to kind of add this on. For A, the thermal efficiency would be work out, which would be 40 joules, divided by Q hot, 100 joules. So that's 0.4 or 40%. B, it would be the 40 joules divided by 200 joules, so 0.2 or 20% efficient. In C, we have 30 joules out divided by 90 joules, so that would be 0.33 or 33%. And for D, there was 50 joules divided by 90 joules, and I cannot do that one in my head. I think they give me a nice number that was easy. So 50 divided by 90, 0.56, or 56%. Remember, efficiency is work WS, or work out, divided by Q hot. Okay? All right. You that a heat engine needs to be a cyclic process. So let's look at putting a very simple heat engine through its paces. Okay, this is figure 21.7 in your textbook. So I have a piston and I've lit a fire underneath it, and I've got a gas in here, and I heat it up. Okay, this would be a constant pressure situation. So it would be isobaric, okay? Come on, go up here a little bit. Now, in this isobaric heating, we have an expansion, okay? Up to this point, heat in. I pop in a piston, I cut off the heat, I lift the mass off, okay? Now, after we've lifted the mass off, we have to have we're going to have a constant volume cooling. So this is a isochoric process. And then once it has cooled for a while, I pull the pin out, and the external pressure compresses the gas and more energy flows out. It's an isothermal process. So if we were to look at this on a PV diagram, okay, we had a isobaric and have an isobaric expansion. Notice I'm going clockwise. Heat's coming in from the hot reservoir. Energy is coming in from a hot reservoir. And we have an expansion. Some energy is going out as work. Okay? And then we have the isochoric compression, no work. The isochoric cooling, heat energy is being pulled out, volume is remaining constant as the pressure is dropping, no work is done. And then we have an isothermal compression. Energy is being used to compress it back. Heat energy is flowing out to the cold reservoir, and we're actually having to do work on the system to compress it back. The area inside the curve here, that's your net work out of the system, the area inside the curve. Because if you think about it, okay, give myself all of this in here. We calculated work to go from point 1 to point 2. That would be the area underneath that curve. Okay, that's going to be work out. But the area that I've hash marked in blue, that's the energy, the work that you have to do to recompress it. So the difference between the black and the blue is the red, and that's the energy that we get out all total from our system. Okay, so heat in, heat out, work being done by the system on the environment, work being done by the environment on the system. The workout is the area inside the PV curve. So Q net is equal to Q from 1 going to 2 plus 2 going to 3, 3 going to 1. Work out is WS 1 to 2 plus WS 2 to 3 plus WS 3 to 1. And work out should equal Q net, Q hot minus Q cold. So let's look at problem 13 on page 594, because I think we just looked at problem 9. So let's look at problem 13. Let me go ahead and scroll this up. Okay. Okay, guys, I think that's as big as I can make it. So look at problem 13. It says, what are Q out, QH, and the thermal efficiency of the heat engine shown in diagram 21.13. Okay? Now, if I look at this, our workout is the area inside the pathway. And it's a clockwise pathway, so I notice that it's a heat engine. So if I look at the area inside there, it's going to be the height, the difference in the height, so change in pressure, 400 minus 100, so that's 300 times 10 to the 3 pascals. The change in volume, okay, the width of that is 200 centimeters cubed, so 200 divided by 1 exp6, so that's 2 2.00 times 10 to the minus 4 meters cubed. So that times 300 exp3, that gives me 60 joules of energy out. Okay? Q hot would be work out plus QC. Well, 60 joules plus 90 joules in this process and 25 joules in that process. The negative sign is giving you direction of flow. It's telling you it's QC. So I have 60 plus 90 plus 25. QH is 175 joules. Okay, guys? Work out the 300 times 10 to the 3 pascals. That chart was in kilopascals. And then the change in volume, the base, 2 times 10 to the minus 4 meters cubed, 60 joules. And QH is going to be work out plus QC. So 60 plus 90 plus 25, 175. Now, to get the efficiency, I'm just going to take the 60 joules and divide it by the 175 joules. So let's do it. 60 divided by 175 is 0.34 or 34%. Okay, so if you're given a PV diagram and it's a very simple one, like this guy, you should be able to calculate work out, QH, and the thermal efficiency. Okay. Now, let's look at, no, we'll come back to one of those problems in a minute. Let me switch over. Okay, let's scroll down here. Okay, a refrigerator. A refrigerator is essentially a heat engine run in reverse and is the device that uses work to transfer heat from a cold reservoir to a hot reservoir. Thus, it's a heat engine running in reverse. Okay? If we look at okay, QH, QC plus work in. Heat flowing in from the cold reservoir and in is work. The energy diagram would look like this. Okay? Work in pulls energy out of the cold reservoir and it dumps it to a hot reservoir. Your refrigerator, your air conditioner are heat engines running in reverse. So external work is used to remove heat from the cold reservoir and exhaust it into a hot reservoir. For refrigerators and air conditioners, we talk about performance. Okay? The coefficient of performance is always QC divided by work in. Okay? K can never be infinity because work in can never be 0. So let's look at problem 19 on page 595. Now, if we look at problem 19, it says the coefficient of performance of a refrigerator is 6. The refrigerator compressor uses 115 watts of electricity and is 95% efficient in converting electric power into work. It says, what are A, the rate at which heat energy is removed from inside the refrigerator, and B, the rate at which heat energy is exhausted into the room. Okay? So let's write down the pieces of information that we've got. We've got a K value of 6.0, and we use 115 watts, which means that we're using 115 joules per second. And then we know that the efficiency of converting electric power into work is 95%. So we have 95% for compressor. So only 95% of that 115 watts of electricity is going to remove energy from the refrigerator. So I'm going to start with 115 joules times 0.95 means 0.95 times 115 gives me 109.25 joules of energy actually going toward powering the refrigerator. And it's a 6 performance, so 6.0. Remember, K is equal to Q to the hot divided by work in. So Q hot, no, it's QC, isn't it? QC, you double check. I'm always trying to confuse QC and Q hot on this one. It's QC, I was right. QC over work in, so QC over work in. So I have 6.0 is equal to QC over 109.25 joules. So QC is 655.5 joules per second. And it asks us, what is the rate at which heat energy is removed from inside the refrigerator? And it's removed at 555 joules per second, because your book always does things to 3 significant figures. And it says then, what is the rate at which energy is exhausted to the room? Well, that means I need QH. QH is going to be 655 joules plus the 109 joules. So 655 plus 109, so 765 joules per second. Okay, guys, camera work here. Okay, so K is equal to 6. We were delivering 115 watts. So that's 115 joules per second, and that compressor is 95% efficient. So 115 joules times 0.95 gave me 109.25 joules. Your book's going to round that to 109. K is equal to QC over work in. So 6 is equal to QC over work in, or 6 is equal to QC over the 109.25. So QC is 655.5. I should round that to probably 656. Okay, so 655 joules is being pumped out of that refrigerator every second. QH is QC plus work in. So that 655.5 joules plus the 109 joules, that's 765 joules per second that's being dumped out into the room. Okay? All right. Now, also want you to notice on this picture, notice the direction of the arrows. Things are going counterclockwise. Counterclockwise means that we've got a refrigerator. Okay? Clockwise, heat engine, counterclockwise, refrigerator. So if you looked at 20 there, and it asks you what is the heat extracted from the cold reservoir and the coefficient of performance, okay? We'd again, this is heat being evacuated. And we got two adiabatic processes. We could go through that whole chart again. Okay? In adiabatic processes, only work is being done, no heat. And we've got heat out, we've got work being done on the system, work being done by. So 119 minus 78. There's 41 joules of work flowing in and 105 for the heart. So Q coming in from the cold reservoir is 146 joules. Okay? So if we look at problem 20 there, we've got QH is 105 joules. Work in is going to be minus 119 joules plus 78 joules because it's cyclic. So that's 41 joules. The negative sign there is telling you that it's work going in because it's WS. Okay? And that means that QC has to equal, Q hot is equal to QC plus work in. So work out was 105 joules. That has to equal QC plus the work in, which was 41 joules. So 105 minus 41 says that QC is 64 joules. So K is equal to 64 joules divided by 41 joules. 1.56 would be our K rating. Okay? So QH was 105. QS was the sum of the two Q's, minus 119 plus 78. We get minus 41. That tells us the work was flowing in, so work in was 41 joules. QH equals QC plus work in. So I get QC to be 64 joules, and K is equal to QC divided by work in, or 1.56. Okay? All right. Now, I want you to remember that there can never be a perfect heat engine. One that converts 100% of heat into useful work. Because if a perfect heat engine were used to run a refrigerator, a perfect refrigerator, you could get heat floating from cold to hot spontaneously, and that violates the second law of thermodynamics. You can never have a perfect heat engine, okay? Because this can never happen. So, thinking about refrigerators and heat engines, the second law says that there are no perfect refrigerators with the coefficient of performance K equals to infinity. And there are no perfect heat engines with an efficiency of 1. things that we know then at this point is that heat engines and refrigerators exist. We know they must be closed cycles, that the change in thermal energy for a complete cycle has to be 0. There is no perfect heat engines or refrigerators, and heat engines will always exhaust heat to a cold reservoir, and fridges always use external work to move heat from a cold reservoir to a hot reservoir. Okay? Questions we have left to answer. How high a thermal efficiency can you get for a heat engine? Realistically, is there a limit on thermal efficiency? The answer is yes. And is there a limit on the coefficient of performance of a fridge? It's got to be yes. Okay? So, here we go. We're going to start thinking about real heat engines. Work out equals the work from expansion minus the absolute value of the work from compression. Okay? So if this is the work from expansion, the gas expanded, Ws is going to be positive here. Okay? If you look at the area under here, the work from compression, it's negative. The net work done in this heat engine process is then the area inside the curve. The difference between the expansion and the compression. Now, handy dandy little table. Okay, great little table. For an isochoric process, okay, volume is constant. Work Ws is 0, heat is N C sub V delta T, and the change in thermal energy is equal to Q. Isobaric process, isothermal process, adiabatic process, and there's the ideal gas law. Okay? If you got any process, you know that work Ws is always equal to the area under the curve. And the change in thermal energy can always be calculated as N C sub V delta delta T. Now, this was a little bit different than the one you saw in chapter 19 at the end of the chapter, because now we're working with W sub S, not work external. Okay? So be careful. Make sure when you read a problem in the homework or on a test, whether it's asking you for WS or work external. So let's look at Stop and Think 21.3. Okay? And see what we can do with this Stop and Think problem. Okay, Stop and Think 21.3. So it says, what's the thermal efficiency of the heat engine? Okay, so we have 4,000 joules in. To figure out the thermal efficiency, all we really need to do is get the area inside there. So if I want to get the area inside there, the base is 0.1 meters cubed times the height, and it moved 20,000 divided by 2, that's 2,000. Okay? So to get the thermal efficiency, all we're going to do is take work out, which is the 2,000, divided by QH, which is 4,000, and we get 0.5 as the efficiency. So the answer to this Stop and Think is B. Okay. You ought to be able to do that. .4 I know pressure, volume, temperature. So I should be able to calculate moles of gas using PV equals nRT. Now, for .1 I know the volume and the pressure. Since I know volume, pressure, and it's an isochoric process, I can get the temperature there at .1. Knowing the number of moles, then I can figure out what the points are all the way around the curve. As long as I know pressure, volume, and temperature from one point on my graph here, I can figure out pressure, volume, and temperature for everything else because I know the volumes at all the points, I know the pressures at all the points, I can get the temperature at all the points. Okay? So I know that the area inside this curve would be the amount of work out because this is a heat engine. It's running clockwise. If it was running the other way, it'd be counterclockwise, and the energy inside there would be the work that I had to put in. Okay? Now, if we start looking at this, step 1 to 2, this is an expansion. So that's work done by the system on the surroundings, so that's going to give us a WS that's positive. 2 to 3, no work done. 3 to 4, we're having a compression. Work is done by the environment on the system to compress it. So this would be a WS that is negative. Okay? We know no work here, no work here. Now, let's look at problem 14 here at the end of the chapter. It says the heat engine in problem 14, which is this one, okay, is a closed cycle which consists of 4 individual steps. The work done by the heat engine per cycle is the area enclosed in the PV curve. So work out is equal to 400 kilopascals minus 100 kilopascals. And they really should have written that as 400 times 10 to the 3 minus 100 times 10 to the 3 times 100 times 10 to the 6 meters cubed, which gives you 30 joules. Okay, so 100. Yeah, they should have put times 10 to the 3 in here. Okay, guys? It says the heat energy leaving the engine, QC, is equal to 90 joules plus 25 joules, so 115 joules. Let's see. See, they didn't give us that directly on that problem. The heat input is calculated, then work out is equal to QH minus QC, or QH equals QC plus work out, or 115 joules plus 30 joules, 145 joules. The thermal efficiency is equal to work out divided by QH, so 30 divided by 145, or 0.207. Okay? Practical engines have a thermal efficiency between 0.1 and 0.4, so it's possible. Okay? Now we're going to look at problem 57. How am I doing on time here? Okay, I've been recording for an hour. Now we're going to look at problem 57 and then we're going to go over it. Okay? Now, if I look at problem 57, it says, okay, figure 21.57 shows the cycle for a heat engine that uses a gas that has a gamma equal to 1.25. The initial temperature T equals 300K, and this engine operates at 20 cycles per second. What is the power output of the engine? So let's figure out what it is for 1 cycle, then we can figure out what it is for 20 cycles, and then get us cycles per second. Energy output per second. What is the power output of the engine, and what is the engine's thermal efficiency? Now, when I look at this, when I go 1 to 2, that's isothermal, 2 to 3, that's isobaric, 3 to 1, that's isochoric. Okay, so this is a really simple 3-step process. Now, what I need to do is I need to calculate the Q and the WS for each one of those portions of the curve. And one thing I want you to notice is they don't tell us what Pmax is. We do know what V2 is, and we know what V1 is, and we know it's isothermal. And they told us what the temperature here at T1 is, and that's going to be the same temperature at T2. So the first thing we're going to have to do is get the pressure Pmax there, okay? So, flip your book, make sure you got this open, and let's follow our way through this problem. Now, if we look at it, okay, we've got a closed cycle process. 1 to 2 is isothermal, 2 to 3 is isobaric, 3 to 1 is isochoric. So we need to find the conditions at point 1, point 2, and point 3. So at point 1, we can use PV equals nRT to find N, and we get N, the number of moles, to be 0.0244. And we're given that gamma is 1.25, which means that it's not monatomic or diatomic, it's something else. So C sub V is equal to R over 1 minus gamma, and in this case, it equals 4R. And C sub P is equal to C sub V plus R, or 5R. Now, on a test, I wouldn't give you something that was a weird gamma, okay? So if I look at point 1 to point 2, the isothermal process, I can use P1 V1 equals P2 V2. So P2 is V1 over V2 times P1. So 6 divided by 2 times P1. So 3 times P1, and P1 was 1 atmosphere, so we get 3 atmospheres, or 3.039 times 10 to the 5 pascals. At point 3, 2 to 3 is isobaric, so we find that the temperature at point 3, so we're going to use V2 over T2 equals V3 over T3. Solving for T3, we get 900K. So now I've got pressure, volume, and temperature at points 1, points 2, and point 3. For 1 to 2, the isothermal process, work is P1 V1, natural log of V2 over V1, or minus 66.8 joules. Q is equal to WS minus 66.8 joules. Okay? For our 2 to 3, our isobaric process, WS 2 to 3 is P2 delta V. So P2 V3 minus V2, 121.6 joules. So that's energy flowing out. Okay? And Q is N C sub P delta T. So 608.3 joules. Process 3 going to 1, the isochoric process, work is 0. Volume is not changing. The Q is N C sub V delta T minus 486.7 joules. So to find the work per cycle, I add up the work for the 3 steps, and we get 54.8 joules. The Q per cycle I add up the Q's from the different steps, 54.8 joules. They should be the same. Okay? Now, the work out per cycle is WS per cycle. That's at 54.8 joules per cycle. So it's operating at 20 cycles per second. So 54.8 joules per second per cycle, 20 cycles per second. That's 1,096 joules per second, or 1,096 watts, rounding to 3 significant figures, 1.10 kilowatts. Now, looking at our cycles up here, okay, negative, negative, positive. Only 2 to 3 is a positive, okay, of 608.3 joules. That's Qn, because it's positive, that's the heat energy flowing in from the cold reservoir. Okay, so to get the efficiency, I'm going to take WS divided by QH, 54.9 divided by 608, so 0.0901, or a 9% efficiency. Okay, not super efficient, but that's okay. Okay, now I'm going to skip the Brayton cycle, and that brings us to limits of efficiency. So I think we've hit enough of this chapter for right now, and that means that next week in class we're going to finish off this chapter, getting ready for your first test.